My lecture is a little bit different than the ones that precede that because it's focused on air data probes or pitot heating systems for ice protection, but in an system engineering side. This presentation is not a formal academic presentation, but it's a view of a system engineering, okay? Just a word about myself. I worked 10 years at Embraer and finished my PhD in 2008 in ice protection system simulation and opened a small business, and specializing in thermal and aerodynamics and combustion engineering. The business is located in São Paulo. These are my partners. They are specialized in heavy industry. In Brazil, we don't have a big aeronautic market, so we do since industrial burners, heat exchangers, but also aeronautics. So Marcos and Francisco are from combustion area, and we work with heavy industries also, okay? And those are the clients. You can see that you have some aerospace clients that we have, Navy, Hartzell, some American companies, Embraer, but also you can see that we have as a customers Petrobras, Vale, Braskem that are from heavy industry side, okay? So, talking about our subject here, I will give you a little introduction, and after that I will make some very simple analysis. These are not theses or very complicated, but day-by-day calculations that system engineers they do during their work, just to have an idea about the limitations and about the challenges that when designing ice protection for pitot tubes, okay? So the pitot tube usually is fuselage mounted, and it has some consequence that you have a different angle of attack for the pitot regarding the aircraft. You also have a different liquid water concentration at the pitot tube location relative to the cloud. So you can have a higher liquid water concentration in pitot location or lower, depending on the streamlines around that, near that. And in order to have the lecture or the measurement of the pitot tube available in all flight conditions, all weather conditions, you should protect against ice formation. Okay, so usually the pitot tubes, they are heated. Most of the heaters are located in the tip of the probe, but also in the body. And because if you have accretion of ice in the body, it will affect the lecture or the measurement of the pressure of the pitot tube. And you can also have ice formation by liquid water, or you can block the probe by freezing rain. But also you can have ice crystals come from the far stream and blocking the probe. So it's a little bit different than icing on wings, because the ice crystals can block the probe. It doesn't stick to the probe, but it can block. So it's a little bit different than the usual structures, the usual wing ice protection. The certification specifically for the pitot tubes is not only the FAR 25 sections or Appendix C, but is specifically defined by a TSO, the Technical Standard Order, the C16 version A. And today we have the C16A referring to FAR 25 Appendix C, and also a British standard document. But the future versions of C16 may refer to a new standard that will be developed by SAE, okay? So when designing the probe or the ice protection of the probe, the main challenge is how can I design a probe that can be adequately ice protected or that can work under ice conditions. And the other question, how can I prove that? So I designed the probe, take into consideration the standards and rules, regulations, but I need to prove that I'm complying with these requirements. How can I do that? Usually, the means of compliance is or you do a simulation analysis or you do a test. The test can be done on ground in a lab like you have here or in flight. If you are going to test in a tunnel, that's the question that is important to copy here. It's how can I prove that my tunnel is reproducing some flight condition or some actual operation? So I need to use some scaling rule or similarity principle to demonstrate that my tunnel is operating in a or reproducing an ice condition found in nature, okay? So, I put together this presentation basically to compare the regulations or the standards, because it's amazing the amount of regulation or standards that you have for probes. It's not like aircraft wing ice protection. You have several rules and standards. So it's interesting for the guide or the engineer that is designing to understand the criticality of each standard. You should compare to know if your design is compatible or is adequate for the operation, okay? And also, if you are going to test in an icing tunnel or wind tunnel, you should have some similarity rules to follow, because your tunnel will not have the same speed or or not have the same temperature. Like we're discussing here that the tunnel only reaches 50 meters per second or cannot go below minus 25. So how can I test more conditions? Do I need to increase the water content? Do I need to change the median drop diameter? What do I need to do to prove that my tunnel is reproducing the reality? So I'm kind of trying to collaborate to the discussion and trying to make my contribution to the team here. So it's only engineering point of view. It's nothing as scientific as the other presentations were. So the main references, as I said before, the technical standard order. So basically, the technical standard order is a document that the supplier of the probe should follow. It's almost a certification of the probe. You have the certification of an aircraft, and TSO is the certification of the probe. It's very specific. You have fuel in an aircraft. It's not for every equipment. So if the manufacturer proves or demonstrates that TSO is compliant with TSO 16A, he can sell the probe. He can sell directly the probe to the customer. It doesn't need to sell the aircraft manufacturer. So it's very different world. We are talking about probes here, not aircraft. So particularly this TSO refers to SAE aeronautical standards of 8006, which is basically how to manufacture, how to control the quality, or whatever, how to provide the probe according to requirements, okay? But it also mentions two other standards or regulation, the 425 Appendix C, and also the BS2G 135 for icing conditions, okay? The previous version of C16 didn't have the BSG standard, okay? So future TSO can refer to the new SAE standard. It's not defined. SAE is developing this new standard. FAA can accept or not, or ANAC can accept or not. It's a standard basically with all the engineers of icing field that put together a very good document, by the way, okay? It's not ready yet. People are voting for the standard. It's not published yet by SAE, but it's almost there after 5 years of discussions. Okay? So basically, the first comparison you can do is comparing total air temperature versus liquid water content. It's very simple. There is no calculation behind this plot here, but it has some information. It's not complete waste of time to compare that, because as your total air temperature decrease, the convection increase, your delta T will increase between the probe and the atmosphere. So there is a correlation here. And also, if you increase the liquid water content for the same impingement or water catch, you are going to evaporate more, you need to evaporate more water. So if you think like that, so this corner should be like more critical. So you have here, this is FAR 25 maximum continuous, that's intermittent maximum. This is EASA, or the former GAA conditions. They didn't publish that. Only in 2007, there was a presentation from a GAA guy that presented that in a congress. But everybody in the industry knows that this GAA standard was suggested to manufacturers to qualify the probes, to certify the probes. Here is the BS2G standard. You see that's very far from that's the test 2. This is the test 1, the 2 points. This is only supercooled liquid water, okay? And you can see that the condition of the BS2Gs is more critical regarding the evaporation. It's not so critical regarding the convection, but keep in mind that evaporation generates more heat demand than convection. So this axis here is more important than this one. So, talking about means of compliance, you have flight test. So, if you are going to fly, it's expensive. And you cannot find all the icing condition as you want, because it's hard to find the ice condition. It may be you go 1 time, 2 times, 3 times and find the same ice condition. So you need some kind of meteorological help for icing hunter to cover the envelope. But it's not easy. It's not easy. And also, in flight condition, you cannot control the variables. It's not like a tunnel that we are doing here, that you control everything. In flight, you cannot control that. So maybe you need to test 1, 2, 3 times to get a good data or something like that. So if you do an icing tunnel test, on the other hand, you control everything. It's not cheap, but it's less expensive than flight. It's safe, but it has some operational limits for speed, for static air temperature, for liquid water content, for medium diameter, volumetric diameter. So it's also, you should, as has been said here before, you should know your limitations of doing icing tunnel test. You should know your tool and use it wisely. Analysis and simulation, yes, you can use that. However, you need to validate. You need to validate both ice accretion or thermal anti-ice simulation or de-ice simulation. They are not, how can I say, very standard simulations. You need to prove that your simulator are doing the job. So you need to spot check with flight tests and tunnel tests. So with a simulator that is validated, you can cover all the envelope. That's why it's important to have a simulation tool. You can cover all the corners of the envelope. That's very hard to get in tunnel or flight test. But it's important because maybe they are most critical conditions. So you need to have a simulation tool, a validated simulation tool. So, talking about the new standard, it's a very brief summary here. It's being discussed to include also the supercooled liquid. Was in the previous standards, but now you have ice crystals, mixed phase icing, and rain, freezing rain. So you have more conditions, okay? And at the same time, the standards for the probes, this standard is trying to make rules or make procedures to do similarity between flight and tunnel, to give some guidance. Okay, the engineer has the last word, so can do more than that, but that's the minimum. So just to show here, mainly Gerhard, the new condition for ice crystals has minus 60 conditions, minus 70 conditions, which is well below the 425. Well below the Airbus or EASA conditions. So the new standard, you cover that. And another innovation here, that you have class of aircrafts. Because the aircraft, they fly at different speeds, different altitudes. So general aviation, turboprops, business jets, large airplanes. So you can see here that the number 4 is always the critical one. It's for the large airplanes, okay? So the test also gives you the static air temperature, icing, water content, because we are talking about ice crystals, not liquid water. The diameter, altitude. So you need to simulate everything in the tunnel. If you look at that, maybe your tunnel doesn't reach the pressure that is equivalent to 45,000 feet. You need to simulate that in the tunnel. So that's why the similarity rules, they are important. because those conditions are very extreme. So, talking about the limitations, you can have altitude limitation, or you can have airspeed or static air temperature limitations. So basically here, for the altitude limitation, you keep the same true airspeed, so same total air temperature, and same static air temperature. That's the purpose of their standards. For the airspeed or static air temperature limitation, so you cannot go so low in temperature, or you have maximum limits for speed. You need to change or to keep the same liquid water contents or water catch. Actually, the water catch. Water catch is the velocity versus times the liquid water content. So you should keep the liquid water catch or icy content, icy catch. So one proposal that I'm making here is not to evaluate standards or not to make similarity rules based only in numbers or with no models behind. My thesis here is that a simple model is better than a no model. Okay? So if you take a very standard model that's published by SAE, so it's zero-dimensional, its collection efficiency is 0.85, the surface is fully wet, you have only a thin water film on that. You're talking here to have effects of convection, water vaporization, water impingement, only that. You don't have icing, melting or solidification or something like that, or you don't have radiation. In this case here, in this standard, it's only supercooled liquid water. Okay? So now we can compare in a different way. We can compare water catch instead of liquid water content, and we can compare power density. That's heat flux, basically. And this unit is very strange. Okay, sorry for that, but it's a watts per inch square. It's a mixed, but it gives you a good number, a low number, so people from the industry use that I'm using here. I could use the other ones, but just for the area, to keep the tradition. So this is supercooled only. This BS2G, it's still the most critical one regarding heat load or heat demand. For the water catch, also is the BS2G. So, this is, I think this FAR, 25 Appendix C, continuous maximum. This is FAR intermediate maximum. This EASA conditions. And those green ones are the new conditions that are proposed for liquid water content, the new standard, okay? So a little exercise here. I'm just checking if the rules proposed by the new standard is conservative or not. And so for the altitude limitation, if you apply the rules, it's okay. The temperature of your surface, it's below the temperature that you would find in our actual condition. However, for the other two limitations, and the speed and altitude limitation together, why I put the altitude limitation together here? Because the tunnels, they don't go too high in altitude. and then they depend actually of the true airspeed, because you have a Venturi effect. So the pressure there is dependent of your speed. Okay? So in those cases, it's not conservative, or the trend is not conservative or is marginal. So in an actual test, if you are going to follow these procedures or scaling rules, you also need to decrease the probe power. So that's the assessment that the engineer should do. So I follow the rules, but the rules are not conservative. What can I do more? So let's decrease the power of the heaters by 20% or 10%, get some margin. That's a very standard model. Huh? This is standard, is published by SAE. I'm not proposing anything strange or... So, I'm trying to go further than SAE model, and this is a proposal to use only evaporative cooling. So you don't have impingement, you just evaporate water, and you have a surface temperature, and it gives that. And if you have a power heat flux there and some water, what will be the surface temperature? That's your question. Because in evaporative cooling, if you evaporate more water, you decrease the surface temperature. At the same time, you decrease the heat transfer coefficient because you are in a lower Reynolds, and you also have the effects of external pressure. So the driving force will increase if you decrease the external pressure, or vice versa. Okay. So it's the same. The assumptions are the same. And only you have here a convection and water vaporization, no impingement at all. So no impingement, no ice melting. And this is very standard from Spalding 1962. We were talking about Spalding yesterday. Anyway. And this is first law. You can rearrange terms here. The way he did in the past was you can have the BM, that's the driving force here. This is mass fraction in its surface, mass fraction in the gas free stream. That's in the surface. So this is non-dimensional driving force. And the relation between your flux and your resistance is given by the first law. So you can couple the mass and heat transfer in one equation, okay? So you have here Lewis analogy, like Professor Sheriff said, so you can correlate mass transfer coefficient with heat transfer coefficient, so this GM, GH, so you by Lewis number. And you can see here that the mass fraction also depends on ambient pressure, vapor pressure at surface, or at far stream or at surface. That's why you have I here, but it also depends on the external pressure. So this is non-dimensional driving force. This is flux time resistance. And this is flight condition at 20,000 feet, Mach 0.44. So your surface temperature is right here. And if you test in a tunnel, the tunnel will give not more 20,000 feet, but it will give you 5.1 kilofeet. And yes, you can reproduce the same speed. Let's simplify here. Okay, so this tunnel has a capacity to go up to 0.44. In this case here, we can see that the tunnel condition is colder, the surface temperature is colder than the flight condition. Oh, it's okay. I can say that's conservative, okay? So I did the same exercise here for the rules, and as the liquid water evaporation is very important, so the evaporative cooling presented the same trend than the previous complete model from SAE. So what are the trends? So the first procedure for similitude or testing or scaling rule is conservative, gives lower surface temperature, and the other two for true airspeed and static air temperature limitations, that's limited here. You can see that I limited 35 instead of 40. I could put a number here, 25 if I want, and instead of 135.5, I put 90. Arbitrarily, I put 90, but I could put 50 or 25 or something like that. So I didn't go very far from the original numbers, so the numbers here also didn't vary much. But it's just an exercise in showing that the temperature is increasing instead of decreasing. So it's the same trend. So we are getting there. I'm almost finishing. Okay, don't sleep. So I put here it's the same evaporative model, but I included here the water impingement effect and ice melting effect. Okay, so when ice melts, it needs the latent heat from external source. When it freezes, it's the opposite. Okay. So I had to state that the probe, inside the probe, is minus 5 C. I could put like 0 C, but minus 5 I think is very conservative. Okay. Actually, we need a complete thermal analysis to determine that temperature, 3D, water catch. So this is very simple. I just showing trends here. Okay. So this is very important because you can see here. One axis here is the total water catch, as we had before. So the water management here is more critical. So how you are going to drain your water that enters in the probe, that's very important because it can cause problems anyway. And it's not a matter of heating, evaporating, it's a matter where the water is going to stay or going to drain, okay? And heat load becomes more critical as the power density or power demand increases. So the circles, the red circles, they are the freezing rain conditions. You can see that there is no much power density demand, but you have a lot of water. You have. And you can see that some EASA conditions also demands a good water management. And that's another point. If you are concerned about water management, why are you going to test an icing tunnel? You should think about that. Could you reproduce that in a other chamber or other test facility? That will make cheap your test. So there are some consequences of that plot that you should take attention, pay attention. If you take a look in the supercooled liquid, is right here. So a lot of power demand, but you have not much water as the rain condition. So they are all here. And that's the new standard conditions, the light blue circles. And the stars, they are the BS2G. Again, this is a good standard. Very good one. And if you see the mixed conditions plus crystals, they are the green ones. So the new standard is really going to extremes. It's very condition with a lot of water and a lot of power demand. So it's critical both ways. So the ice crystals going into the probe is very critical. And you can see that the BS2G is not that far from there. If you have some design margins, you design for that, but some margin of safety, maybe you are right here. So, this is the same exercise. This is super cooled, no icing crystals, but just to test if the thermal balance is okay. And it gave this practically the same trend. So that's just show that in these cases also you may need to increase the power density or decrease the power density to decrease the surface temperature to be more conservative. So, conclusions. So, even a simple model is better than a no model. You take 15 minutes to do the model, just evaluate that. It's better than compare raw numbers, you know. And the modified evaporative cooling model to deal with crystals and water catch did the job, you know. If you included there the additional heat or the additional enthalpy demand, it does the job. So this is another conclusion, that's if the standard doesn't provide you or is providing you a margin of safety that's not acceptable or is very marginal or has not a good trend for you or you're not secure, decrease the power to the probe during the test and make some margin, make some room for your design, okay? So it's not here, but also you have the conclusions of comparing the standards. You'll see that the new standard is going to extreme conditions. I hope this is out in next months or weeks. And you'll see that the BS2G standard is very good. That's another comparison that you can do. Okay? And for next steps, and I'm talking in a university here, so you may have some interest to develop some models here. Because I only develop models for my customers. If I don't have demand, I will not develop. But you can. You can develop and search for a user or search for somebody that will fund your research or something like that. Okay? So you need to study the transient, because the probe is basically transient, because you can have a peak of heat load demand, and how much time the ice will take to melt. Maybe you have the proper heat power there in the probe, but if you have a lot of water coming into the probe, you have a transient response that's not adequate. So you should have something like the transient or dynamic modeling You need also to study the temperature inside the probe. It's a completely different problem than studying the external. I think you are doing a very nice work here regarding this one. Also, it's very important to understand the dynamics of water over the surface, inside the probe, through the drains, okay? It's very important. And it's also important to take those 3D results and translate it to 0D, so the engineer can use it in a day-by-day calculation. Not too fancy. So, this is basically water, liquid water impinging in an airfoil. It's a simple NACA 0012. We did that in our offices as a prototype. We are trying to develop it as a research or innovation. It's innovative because it's coupling CFD with water dynamics. Usually CFD codes, they don't have water dynamics. You have only airflow or gas flow or liquid flow in a separate way. But this is coupled, okay? So this is the thickness of a water film, and it also has a surface tension model that makes it to turn into rivulets, break it down into rivulets. So, why this is important? Because for ice accretion, in a glaze ice accretion, like Professor Sheriff said, it's very important to know the water, because the water doesn't impinge and freeze on impact. It runs streamwise and freezes somewhere. When the transition occurs or where there is an increase in heat transfer coefficient, whatever, you need to know the path of water. And as Abdullah said, the swept wing, this is very complicated. This is a straight wing. If you have a swept wing, it's much more complicated. The streamlines, they are not aligned. They have one direction in the leading edge, and they make a turn, and the shear line is different than the streamwise, the potential flow. There is a twist between the streamline of this external flow and the shear line. It's very hard. So if you don't have a surface model for water, it's hard to predict anything. It's the basic brick. This is the basic brick for glaze ice. You need to have that. But also it's the basic brick to have de-icing or anti-ice ice protection, because you need to know how much runback you are generating in that configuration. And if you start forming runback, it will not evaporate anymore. You are going to generate runback ice after your protected area. So this is why this is important, okay? And for pitot tubes, this is important also because it has 3D structure. These are some results for freezing rain or a lot of water. They are not so scientific. I did that for demonstration only. It's a prototype, so you can check here. This film velocity magnitude, okay, that's thickness, different case, less water. This is another case, more water. So, as I said before, it's important to have simulation tools to cover the operational envelope, but also there is a need for the validation tunnel or flight. But again, it's important to have a tool that can reproduce, because it's cheaper to run, and also it it's more flexible. So I'm not telling that the tunnel is not important. It is. If you don't have the tunnel, if you don't have the flight test, you are not going to have simulation tools. And the important about your tunnel that is very well equipped with cameras, and you can film all the water run back on that, and you can see the droplets splashing. So it's very important because it's small, it's controlled. To develop models, it's a key. Okay? So, thank you very much.